Hello guys, welcome to my YouTube channel Physics Prince. My name is Deepak. I'm going to teach you all 9 subjects of physical science in detail. My courses are absolutely free of charges. My courses are going to help the students who are preparing for CSIR, NET, GATE, NT exam, PhD exam, SET exam, TIFR, Jest, IIT-Jam and other exams related to physical science. Okay, so this is the lecture number 12 of condensed matter physics, in which we will study free electron theory, classical theory and quantum theory. Okay, uh, and also guys, I would request the students who haven't subscribed my channel yet, please subscribe my channel and also share the details of it to your friends, so that they can also watch my free live lectures and get benefited from it. Okay, so in last lecture, my class was ended automatically when uh, I was explaining Debye theory. Okay, the and uh, and now I'm going to start from where it was ended. Okay, so let's get started. So guys, last time I have explained Debye theory, right? And I have given this Debye theory, and in which we have found Cv is equal to, that is 3r, which is 3r into theta d upon t, fd. Okay, where, so I would request you guys, please watch my previous lecture for detailed information. Okay, so Cv equal to 3r theta d upon t fd. Okay, where fd is the Debye function, theta d is the Debye temperature. Okay, and fd value is fd, this value is 3t upon theta d to the power 4 integration 0 to theta theta d by t e to the power x to the power 4 dx upon e to the power x minus 1 whole square. Okay, 3 into t upon theta d, right? And where x value is h cut omega d upon k, h cut omega t upon kt. Okay, where omega d is Debye frequency. Okay, and omega d value is this one, h cut omega d upon h cut omega d upon k, that is Debye frequency, Debye frequency. Okay, and theta d is Debye temperature, and theta d value is theta d value is no, we have done mistake, right? Sorry, this is theta d guys, theta d, and this is called Debye temperature. Okay, Debye temperature. Okay, and omega d is Debye frequency, omega d is Debye frequency. Debye frequency. Okay, and x value is h cut omega d upon kt. Okay, so this is the important formula, guys, you need to note down. Okay, Cv equal to 3r theta d upon t into fd. Fd is the Debye function. Okay, Debye function. This is FD. Okay, divide function. Well, this was I have already explained in my previous lecture. So now I will explain this value of CV at different temperature. Okay. Well, so now at high temperature, guys, at high temperature, first case 1 is at high temperature, CV is going to be 3R. Okay, and case 2 at low temperature, CV is going to be 12 by 5 pi to the 12 by 5 pi to the power 4 R T upon theta D whole cube. Okay, this is very important. Okay, this is at low temperature, guys. Okay, so CV value is 12 upon 5 pi to the power 4 R into T upon theta D whole cube. Okay, so this is important, and from here you can see CV is proportional to T to the power Q, and CV is also proportional to 1 upon theta D, 1 upon theta D cube, right? 1 upon theta D cube, 1 upon theta D cube. So very important, right? So, or we can write CV is equal to D T cube, and where value of B is 12 upon 5 pi to the power 4 R upon theta D cube, R upon theta D cube. Okay, so these are very important results, guys. Okay, you must note down and memorize it, guys. Okay, well, and now this Debye theory has successfully explained the specific heat of the solid. Okay, and at high temperature we can see it is matching with experimental values, right? At high temperature CV is constant, that is 3R, and at low temperature CV is proportional to T cube, right? Which are experimental value, and Debye theory explained it successfully. Okay, so now I'll make a graph. Okay, and which matches with the experimental value. Okay, so the graph is, this is Kelvin versus CV. Okay, and this graph is going to be like this, guys. Okay, this one, and this matches with and matches with experimental value, right? So this is the graph between CV and T of Debye, right? So Debye has successfully explained the specific heat of the solid. Okay, so this is the graph, guys. Okay, next I'm going to tell you the trick, which is very important, you need to know. Okay, the trick is meanwhile just let me check whether I'm audible or not, then I will proceed further. Okay, experimental value and Debye theory. Yes, I'm audible, so I'm going to proceed further. Okay, so trick is very important trick, guys, and you need to know. So if omega is given proportional to k to the power s. Okay, if omega is given proportional to k to the power s is integer, guys. Okay, okay, omega is proportional to k to the power s. In that case, CV, and we have been asked to find the CV. CV is going to be proportional to t to the power d upon s. Very important, t to the power d upon s, where d is dimension. Okay, very important, this one. Okay, so you need to note down. So this is the one, guys. Okay, so CV is going to be proportional to D upon S. Okay, K is the integer, S is integer, guys, and D is the dimension, 1D, 2D, 3D. Okay, so this is important trick. And now electronic specific heat. We have studied lattice specific heat. Now it's electronic specific heat. Electronic specific heat. Electronic specific heat. Okay, so electronic specific heat, that is CV, is going to be proportional to T. Okay, or CV is equal to AT. Very important. Okay, electronic specific heat is going to be CV proportional to T, and CV is equal to AT. A is the constant, guys. Okay, this one, and here, or this value of CV is, I'll write here, it is for electronic specific heat I'm talking about. Okay, so CV is equal to pi square R KT upon 2EF. Okay, so this is pi square R RK T upon 2EF. E is the Fermi energy, guys. Okay, so from here you can see CV is proportional to T, and also CV is proportional to 1 upon EF, or inversely proportional to Fermi energy. EF is Fermi energy. Okay, Fermi energy. These are very important points. Okay, Fermi energy. Okay, now this is important result, guys. Okay, these are important results. Now for insulator, if we talk about, for insulator means they are in insulator there is no free electrons. Okay, insulator if you talk about insulator, only phonons or lattice vibration. Okay, so in insulator only phonons oblique lattice. So specific heat is only because of phonons or lattice vibration, not because of free electrons, because there are no free electrons in insulator. Okay, so only insulator, if you talk about insulator, so the specific heat is only because of phonons or lattice vibrations. Okay, so in that case, for insulator, CV is going to be B T to the power Q, right? B T to the power Q. B T to the power Q. Okay, and this implies CV is proportional to 1 upon theta d cube, right? Since B is proportional to 1 upon theta d cube, right? Or we can write this is proportional because this is the value of, right? Or B is proportional to B is proportional to theta d cube. Okay, why? Because we know value of B is equal to 12 upon 5 pi to the power 4 r upon theta d cube, right? I have solved here this one. This 12 upon 5 pi 4 r upon theta d cube. Okay, so 12 upon 5 pi 4 pi to the power 4 r theta d cube, right? So this is important result. And yeah, now if you talk about metals, so in metals the specific heat is because of free electrons as well as phonons, right? So free electrons and plus because of phonons or lattice vibrations. Okay, so in that case CV is going to be 80. This question is asked, guys, 5 marks question. Okay, so C 80 plus B T cube. Okay, so CV is going to be equal to 80 plus BT cube. Okay, and from here A is proportional to 1 upon EF, right, and B is proportional to 1 upon theta D cube. Very important, guys. This question is asked. This is a in gate. This is gate PYQ, guys. Okay, gate PYQ. Okay, so this is gate PYQ. So we know the value of A, right? Value of A is this one is pi square RK upon 2 EF. EF is Fermi energy, right? And value of beta I have already written. That is, this is 12 upon 5 pi to the power 4 r upon theta d cube, and this is pi square RK upon 2EF. You need to note down that if A and B are constant, right? A is proportional to 1 upon EF, or A is inversely proportional to EF, and B is inversely proportional to cube of theta d, that is divide temperature. Okay, these are very important result, and this question is asked in CSIR net, and this is asked in GATE. Okay, next. This is a trick, guys. So we have got the trick, right? I have already written the trick, that this one CB is T to the, if omega is proportional to K to the power S. Okay, so it is K to the power S, guys. Okay, K to the power S is integer. Okay, so in that case CB is going to be proportional to T to the power D upon S. Okay, D is dimension, guys. So here I'll explain it. So here you can see, suppose we have omega is proportional to K, this means omega is proportional to K to the power 1, right? K to the power 1 is K. So here you can see S equal to, implies S equal to 1. So in that case CV is going to be in one dimension. CV is going to be T to the power this one D upon S. D is one dimension, we are talking about 1 upon S 1, that is CV is going to be proportional to CV is going to be proportional to T. Okay, I'm talking about 1D. Okay, 1D. And similarly CV is going to be proportional to, for 2D, 2 upon 1, right, T square in 2D, and CV is going to be proportional to T to the power D upon S, right, this trick, T to the power D upon S. Here S is K to the power, right? K to the power is 1 only, just K, right? So in 3D it is going to be T to the power 3 upon 1, that is T cube. Okay, so in 1D is T, 2D is T square, and 3D is T cube, if omega is proportional to K, linearly proportional, right? If it is like this, if it is given, if omega is proportional to K to the power 2, here S is 2, right? So in that case in 1D CV is going to be proportional to T to the power 1 upon 2, right? And in 2D, this is in 1D, because T to CV proportional to T to the power D upon S. D is 1, sorry, 2 upon S, right? 2D, we are, yeah, it's correct, 1D, right? So 1 upon 2. And if you talk about CV is proportional to, in 2D it is going to be 2 upon 2, that is T in 2D, right? And similarly, if this is the case, CV is going to be proportional to T to the power D upon S, 3 by 2 in 3D. These questions are very important, and if we know this trick, we can easily solve these questions quickly, guys. Okay, in the examination. So you need to understand it. Okay. Well, now we are going to study free electron theory. Okay, these are very important results. Trick is important. Okay, next is free electron theory. Just give me 1 second. Okay, free electron theory. Or it is also called classical theory, guys, and which is field, guys, but it's very important. We have studied it, or it is called Drude models as well, Drude's model. We have already studied in class 11th and 12th. Okay, so this is Drude model also. It is called Drude model. Okay, so it is the theory for conductor, right? So this is, suppose this is a conductor, and there are 3 electrons. Okay, and if it is attached with any potential, right, electron will move, and current will flow, right? This is the one, and potential is V, right? So there is time relaxation time, mean free path, right? This one we have already studied in class 11th and 12th, right? Like for example, if you talk about mean free path, means the distance covered by the particle, the electron in 2 consecutive collision, right? Or also time interval between 2 consecutive collision, that is relaxation time, right? This we have studied. So here we know, guys, this is J is proportional to E. Okay, J is proportional to E, the current density is proportional to E. Okay, or current density is going to be equal to sigma E. Okay, sigma is the conductivity, guys, very important formula you need to note down. Okay, and here also we know that R is proportional to L, and R is also proportional to 1 upon A. That is, L is length of this conductor, and L is cross sectional area, right? So it means R is going to be equal to rho L upon A, where rho is the resistivity. Okay, rho equal to resistivity, and this is rho, and sigma equal to conductivity. Sigma equal to conductivity. Okay, this is important formula, right? You need to note down, and this is one. Now, according to free electron theory, right, that Vd is that drift velocity of electron is going to be proportional to E. Okay, drift velocity of electron. Okay, velocity of electron is going to be proportional to Vd. This E is the electric field by this potential. Okay, so this is going to be Vd is proportional to E. Okay, and so it means Vd is going to be equal to mu E, where mu is, guys, mobility. Okay, mu is mobility. Okay, so here in free electron theory we have found current is going to be important formula, NEAVD. Okay, NEAVD. V is the drift velocity, Vd is drift velocity, is the area cross section, is the charge of electron, and is the uh, electron density. Okay, NEAVD. This is important, and current density is going to be equal to I upon A, right? So that is going to be NEVD, important formulas, right? And J, as we know, J equal to sigma E, right? J equal to sigma E. Sigma is the conductivity here. J equal to sigma E, right? So from here we can put the value of sigma. So this is going to be J sigma E. Sigma E is going to be NEVD. NE and VD value is mu E, right? So mu E, mu E. EE will get cancelled. This implies sigma equal to NE mu. Guys, this is important. This is the formula for conductivity. Okay. conductivity of conductor. Okay, NEA mu. Mu is the mobility, N is the electron charge, and E is the charge of electron, and N is the electron density. Okay, and this is the sigma, and we know sigma is 1 upon rho, right? Or rho, that resistivity equal to resistivity is equal to 1 upon sigma. So this is going to be 1 upon sigma value is any mu, right? Any mu. So this is 1 upon any mu. This is also important result. Okay, you need to note down. So you can we'll solve many questions using these formulas. Okay. Yeah. Well, now there is one law, that is Wiedemann-Frenz law. Okay, Wiedemann-Frenz law. So that is Wiedemann-Frenz law. Wiedemann-Frenz law. Okay, very important formula. There are questions asked using this formula. Okay, Wiedemann-Frenz law. Wiedemann-Frenz law is K upon sigma t equal to constant, and that constant value is equal to L. L is called Lorentz number. Okay, L is Lorentz number. And K is the thermal conductivity. K is thermal conductivity, and sigma is, we know, that is electrical conductivity, right? Electrical conductivity. Thermal conductivity and that electrical conductivity. Okay, so this is the Wiedemann-Frenz law. Okay, K upon sigma t equal to constant. Sigma is thermal conductivity. My apology. This is, yeah, K is the thermal conductivity and T is the temperature, right? So K upon sigma t equal to L. Important one. Okay. Well, and also experimentally we have found that resistivity is proportional to T. Okay, for metal. This we have found experimentally. So rho proportional to 2, that is metals. In case of metal, that resistivity is proportional to the temperature. Okay, but classically by this free electron theory, we have found P is proportional to root T. Okay, this is not correct. Okay, root T. So this theory failed, right? Next, we are going to study quantum theory. Okay, quantum theory, important one. Quantum theory. Okay, in quantum mechanics, we know, I have already explained quantum mechanics, right? You can check my lecture. Complete course of quantum mechanics is there in the playlist. You can check it. Okay, so there are 29 lectures of quantum mechanics. Okay, so this is the 1D infinite potential box. 1D infinite potential box. Okay, width is A. Okay, 1D infinite potential. 1D infinite potential, and I have already explained the energy of it. Energy of this is En is equal to n square pi square h cut square upon 2 ml square, right? And since we know h cut equal to h upon 2 pi, right? H upon 2 pi, So we'll put the value. So En is going to be equal to n square h square upon 8 ml square, n square h square upon 8 ml square. Okay, and the wave function we know, that is psi nx wave function is equal to, we know that 2 upon L, this is the A, right? So here we are taking A. Okay, length is L, guys. Okay, same thing, width. So 2 upon L, this is sine n pi x upon L, right? N pi x upon L. Sine n pi x upon L. Okay, since k equal to n pi upon L, right? So it means wave function psi n x is going to be equal to root 2 upon L sine kx. Okay, root 2 upon L sine kx. Okay, so and here, right? So now we have k equal to n pi upon L, right? And E is this. So here En is going to be, we'll put, well, n pi L equal to k. So this En is going to be equal to h cut square k square upon 2m. Okay, and now we'll study this at 0 Kelvin, at T equal to 0 Kelvin. So we'll talk about Fermi level and Fermi energy, right? So the energy is like this in 1D, right? This one. Right. This is completely filled. This is NF, guys. Fermi level, okay? This is completely filled. And these levels are completely empty. These levels are completely empty. These levels are completely filled. Okay. So at T equal to 0, Kelvin, the uppermost energy level, this level we are talking about. Okay, the uppermost energy level, which separates occupied levels to unoccupied, unoccupied. Okay, this is the Fermi energy level. Okay, so at T equal to 0 Kelvin, the uppermost energy level, which we are talking about, this level, okay, which separates occupied level to unoccupied level, that is called Fermi energy level. Okay, called Fermi energy level. Okay, called Fermi energy level. Called Fermi energy level. Okay. Next is, we'll draw a graph between energy and f is function of E. Okay, so this is going to be like this. Okay, this is half, this is half, this is 1. Okay, and this graph is at t greater equal to 0 Kelvin. Okay, these are equal distance, not looking, but these are equal. This is half, this is 1. Okay, this is the graph, almost like this. Okay, this one. Now EF is going to be Fermi energy. We are talking about Fermi energy at 0 Kelvin. EF is going to be h cut square k square kf square, right? Kf square upon 2m. Energy we have found here, right? This one equal to h cut square k square upon 2m. Now at Fermi energy level, h cut square kf square upon 2m. So here kf is Fermi wave vector. I'll write this. Okay. So this one, and value of kf is, since value of kf is going to be n pi upon 2l. Why? Because I'll explain in next page. Because let total number of electrons, let total number of electrons, total number of electrons are n. Okay, so it means n is going to be equal to 2nf, because there are even number of electrons, right? 2nf, 2nf. So from here value of nf is going to be n by 2. Okay, so that implies value of kf is going to be nf pi upon l, and nf value is n by 2, so implies kf is n pi upon 2l. Okay, that's why the value is n pi upon 2l. Well, and so E is going to be, EF is going to be, we'll put the value of k square, so h cut square upon 2m into n pi upon 2l whole square. So this is the energy, important one, guys. Okay, this is the energy. Next is here I am going to write where the values of these, right, important values, where nf is Fermi level, kf is Fermi wave vector, Fermi wave vector, kf is Fermi wave vector. Okay, and so here ef we have found, that is h cut square upon 2m kf square, right? And tf we know, tf value is ef upon k or kb, Boltzmann constant, right? This is called Fermi temperature, Fermi temperature. Okay, and pf, Fermi momentum, is equal to h cut kf Fermi energy, right? And vf, Fermi velocity, is equal to pf upon m, that is h cut kf upon m. Vf is Fermi velocity. Fermi velocity. Okay, Next is, so from here we can say EF, very important result I'm writing. EF is proportional to TF, Fermi temperature, and proportional to KF square. Okay, this is important result, guys. And PF is proportional to KF. Okay, and VF, Fermi velocity, is proportional to KF. Okay, Fermi wave vector. Well, here I'm going to make a table which is very important table. You need to learn it and memorize it, guys, because this is going to help you in your examination. Okay, so this is a chart for KF, Fermi wave vector, EF, and density of state, ground state E naught, and N. Okay, so this is density of state, density of state. This is ground state, and this is number density, right? Electron density or number density, right? Well, okay, so this is important one, and I'm going to make it. So if you talk in 1D, KF value is n pi upon 12. We have found it. Okay, very important. And energy value is going to be h cut square upon 2m, and this is n pi upon 12 whole square. Okay, and density of state is going to be proportional to e to the power minus half. I'll tell you the trick, then you can easily understand. And the ground state value is EF by 3, and number density is n upon L, right? Now, if you talk about in 2D, this is going to be 2 pi n by a to the power 1 by 2, okay, or this is h cut square upon 2m, and this is going to be 2n pi upon a, 2n pi upon a, right? This is 2n pi upon a, right? This is all right, and this is going to be e to the power 0, and this and ground state energy in 2D EF by 2, and this is a number density n upon a, number of electron per unit area. If we talk about in 3D, that KF is going to be 3 pi square n by a to the power 1 by 3. This is 1 by 2 and 1 by 3, and this value is going to be h cut square upon 2m, 3 pi square n upon a to the power 2 by 3, and density of state is going to be proportional to 1 by 2. Okay, and this is going to be 3 by 5 EF, and this value is going to be n by v. Okay, number density per unit volume. So this chart is very important, guys. You need to memorize it. Okay, next, density of state, density of state. So that is dE, density of state, dE is going to be equal to dn upon d, guys. Okay, dn upon n is number of electrons, and d, okay, dn upon d, very important. And in case of this Fermi energy, so it is going to be dE is going to be equal to dn equal to 2nf, right? 2 dn small n, okay, nf is n, right? 2 dn upon d. okay, and the range is E to delta I. Okay, so now we'll find this one. We have En equal to n square pi square h cut square upon 2 ml square, right? So from here we can find dE upon dN, right? Small n, small n. So this is going to be n into pi square h cut square upon ml square, right? 2 will get cancelled, 2n, right, will cancel 2, right? So from here this is d upon dn. We need to find dn upon d, right? So this is going to be so d is going to be dE density of state, dE, it is going to be 2 dn upon d, right? And d upon dn we have, so this is going to be 2 into ml square upon n pi square h cut square. Okay, so from here density of state is going to be proportional to 1 upon n. Since we know E is proportional to n square, right? This implies n is proportional to 1 upon root 2, root E, right? So it means dE is going to be proportional to 1 upon root E, or d is going to be proportional to e to the power minus half. Very important. Okay, this one. Next I'm going to tell you the trick, which is very important trick. Okay, so here trick is omega is proportional to k to the power n. Okay, or this implies if omega is given proportional to e to the power n, okay, or k to the power n, okay, this I'm going to do later. First here I'm going to explain this one. If n equal to 1, okay, if n equal to 1, right, so it means omega is proportional to k to the power n, or e is proportional to k to the power n. Okay, and if e is n, if n equal to 1, that implies value of e is going to be proportional to k, right? If this is the case, if e is proportional to k, this is for massless particle, massless particle, massless particle like phonon, photon, oblique phonon. Okay, and also for graphite, or graphene, okay, or relativistic electrons. For these particles, E will be proportional to K. Okay, relativistic electron. And if E is proportional to K square, right? This is for massive particle, okay. Second is for, and this is E is proportional to K square, is photon gas, and third is non-relativistic electron, non-relativistic non-relativistic electron, non-relativistic electrons. Okay, well, this is the one. So if it and massless particle, we know for massless particle, like photon p equal to, they have momentum, right? P equal to E upon C, and h cut k equal to E upon C. Value of p is h cut k, right? C. So that implies k is proportional to that E is proportional to k, right? This is how E is proportional to k, like this one, right? That's why E is proportional to k. And if we talk about that massive particles or mass particles, then or photon gas P is going to be equal to root 2 me, okay, and h cut k is going to be equal to root 2 me. P is h cut there, so this implies E is proportional to k square. Okay, now a very important thing I'm going to explain here, trick. Okay, the trick is here. Trick is density of state you need to find out, and that is going to be proportional to E to the power d upon n minus 1. Okay, if E is proportional to k to the power n, or omega is proportional to k to the power n. Okay, n is integer, guys. Okay, so d is dimension, guys, where d is dimension. Okay, d is dimension. So here so now we can find out by trick, we can find out 2-3 things. Like suppose for 1d, if you talk about 1d, okay, E is proportional to k is given. Okay, E is proportional to k is given. E is proportional to k means n equal to 1, right? That's why e to the power 1 equal to e to the power k to e to the yeah, E proportional to k to the power 1 equal to E proportional to k, right? So in 1d we are talking about, so density of the state is going to be proportional to E to the power d. Dimension is 1 upon k to the power 1, n is 1 minus 1. So this is going to be E to the power 0, right? Here we have find out like this in this chart. E to the power, okay, this is not, this is the different, this is for this 1 k to the power n case. Okay, that is the general case. So now k square, that is for k square, right? Okay, if we talk if we talk about 2d, for this case when E is proportional to k, so de is going to be proportional to E to the power 1 upon, dimension is 2 upon 1 minus 1, so it is going to be E. Okay, right? And similarly, if we talk, if E is proportional to k to the power 2, we are using this trick, guys. Okay, so how we are going to get a density of state if we have given dispersion relation, that is E to the power E proportional to k to the power n, or omega proportional to k to the power. So E proportional to k to the power n is given, implies n equal to 2. So in 1d, density of state is going to be proportional to E to the power, dimension is 1 upon 2 minus 1. This is E to the power, sorry, density of state is going to be n equal to 2, right? So this is e to the power d is 1 upon 2 minus 1. So this is e to the power minus 2. So if we talk about 2d, in case of E proportional to k square, right? 2d, so this is going, density of state is going to be e to the power d is 2 upon 2 minus 1. So this is going to be e to the power 0. If you talk about 3d, density of state is going to be for E proportional to k square, right? We'll use this trick, e to the power d upon n minus 1. So e to the power d is 3 or n is 2 minus 1. So this is going to be e to the power half. Okay, so this is how we'll use the trick. Okay, well guys, also guys, before ending the class, I would request the students who haven't subscribed my channel yet, please subscribe my channel and watch my free live lectures which are going to help you to crack the exams related to physical science. And also guys, share my details and my lectures to the to other students as well, to your friends, so that they can also watch my free live lectures and can be benefited by it. Okay, okay guys, thank you so much. Bye now.